land, this region here near the Welsh border, where they're preserved along long-lived fault systems. And in central England, such as Charnwood Forest, where it's been, I believe. The ages on this graph are mostly uranium-lead zircon ages by iron probe, and typically of uncertainties of around 10 million years or so, and they'll be present on most of the most of the next few slides. So we'll look at them in detail as we move on. Starting in Charnwood Forest, the sequence there consists of the Charnian supergroup, where there's about 3 kilometers of acid to intermediate volcaniclastic sediments. Those sediments of volcanic origin, and these include sandstones and breccias. There are submarine pyroclastic flows, a fauna of this particularly wonderful creature here, which you may even have seen in the field. You see it in the field?
Yeah.
Charniodiscus or something like that.
Charniodiscus.
You saw it. Did you believe it was a fossil?
No.
No. Well, there you go. People who know more about these things than I tell us that this is clear evidence of an Ediacaran fauna, very late Precambrian fauna. Ages of the rocks in Charnwood Forest, there are a few intrusions. Diorite has given an age of 603 million years, and the volcanic rocks within the sequence have given 560 million year ages. And the uppermost part has Cambrian trace fossils. So that suggests that it was folded and cleaved, as you will remember from your structural exercises last year. It is folded and cleaved. Yes? That suggests the cleavage took place in the early Cambrian. Next area, the Church Stretton region of Shropshire, so this sort of little area here. There's the stratigraphic sequence for that region. There is a tiny outcrop of a metamorphic rock called the Rushden Schist, which I have attempted to find with minimal success, because it's obviously smaller than even I thought it was. People have suggested that this is at the base of the sequence, but it's difficult to be sure given the level of outcrop. It's a garnet mica schist and was metamorphosed about 680 million years ago. Then we have the Uriconian sequence. This is about 1 kilometer in thickness, and it appears to be largely subaerial lavas, pyroclastic rocks, and these range in composition from basalt through andesite to rhyolite. Calc-alkaline in chemistry, for those of you who've been doing the igneous class, suggesting that they were erupted in a volcanic arc environment. A rhyolite has a 566 million year zircon age, very, very similar to ages in Charnwood Forest. There's a photograph of the rhyolites at the museum, which is just off the M54. In addition to the volcanic rocks in this region, there is a thick sedimentary sequence called the Longmindian. It's about 6 kilometers thick, largely sand and muds. It forms this hill area on the other side of the town of Church Stretton. The lower part of it is a regressive sequence, marine regressing from marine, and the upper part of it is alluvial. Commonly, the Longmindian is thought to be above the Uriconian, but there have been recently produced zircon ages from tuffs within the Longmindian that suggest it's probably the same age. So the environment that you can imagine is that we have volcanoes forming islands and relatively deep basins in between those volcanoes. So it sounds like a fairly typical island arc in a marine environment. The Longmindians tightly folded, cleaved, and overlain unconformably by Cambrian. So not dissimilar to Charnwood Forest, really. Malvern Hills, just to the south of Worcester down here. There's the sequence for the Malvern Hills. The bulk of the rocks within the Malvern Hills are plutonic rocks, dioritic to granitic, of calc-alkaline composition, again suggesting a volcanic arc environment. Intrusion of these plutons is about 677 million years, and they are relatively weakly metamorphosed so that they have a degree of schistosity, low amphibolite facies. And they cooled from this metamorphism to about 300 by 650 million years ago. The plutons are overlain by volcanics that are very similar to the Uriconian and give an essentially identical age of 566. On the Welsh mainland, in northwest Wales and in southwest Wales, the Arfon group in the northwest, there's about 4 kilometers of rhyolitic ignimbrites and sandstones, and these yield ages of 614. They're overlain unconformably by tuffs that give 570 million year ages, again similar to the Uriconian. The sandstones apparently pass upward into Cambrian rocks. And in southwest Wales, 2 kilometers of intermediate to acid pyroclastic rocks and diorites, and these have yield ages 640 to 590. So there's a very consistent series of ages, a very consistent series of lithologies in these Precambrian outcrops. Calc-alkaline, basalt, andesite, rhyolite, plus their intrusive equivalents, ages between 680 at the oldest down to 560 at the youngest. A rather different assemblage of rock types is found on the island of Anglesey, which in Welsh, with apologies to the Welsh members of my audience, is called Ynys Môn or something like that. And after the Welsh name of the island, the main lithological group on Anglesey is called the Monian supergroup, which are 5 to 7 kilometers of sediments and volcanics that are strongly deformed and cleaved. There has been a very considerable debate in the literature about the age of the Anglesey sedimentary sequence, and furthermore, which way up it is. What most people think is the lower part, but may be the upper part, who knows, depends which way who you believe, is a southeast-derived turbidite fan consisting of quartzites, phyllites, metavolcanics, and the upper part, called the Guna Melange, is an alistostrome. That's a submarine mass slide deposit, gravity slide deposit, that carries really large-scale blocks of a variety of lithologies. In this case, it contains stromatolitic limestones, blocks of quartzite, blocks of greywacke, and blocks of pillow basalt in a muddy matrix. and some of these blocks can be up to a kilometre across, so it's a very large-scale submarine mass slide deposit. There's an example of an outcrop of pillow basalts on Anglesey, and this would be roughly a kilometre-long outcrop. That itself is a large raft within this melange, within this Elizabeth. In addition to the sedimentary sequence, there is a body called the Coadana complex. On the map of Anglesey, that's just this bit here. This is a granitic body that is calc-alkaline in composition and dated at 613 million years, so very similar ages to those we've been seeing in the volcanic rocks within England and the rest of Wales. And this is associated with some high-grade metamorphic rocks that include selemonite facies, gneisses, selemonite grade gneisses. And has been unclear for a long time whether these gneisses represent metamorphism of the metasedimentary sequence, the Mona sequence, or whether they represent basement on which it was deposited. In addition, there is a package of blue schists. That's the yellow unit on the map here. The blue schists contain all your favourite minerals, glaucopane, lawsonite, cyprosite, and as you will remember, indicate high pressure, low temperature metamorphism, typically produced in a subduction zone environment, in a subducting slab, and metamorphic uplift from metamorphism is dated at about 550 million years ago. So not dissimilar to the ages of many of the volcanic rocks we've been talking about. The blue schist locality is at a relatively famous Welsh village, which you may have heard of. It's the sign is on the railway station.
Yeah, we can really read it.
Very recently, the detrital zircon data have been reported from part of the Mona sedimentary sequence that have minimum ages of 500 million years. You can see in these graphs we've got 500 million year zircons, which implies that the sediments have to be younger, or at least some of the sediments have to be younger than 500 million years, implying sedimentation of at least some of this sedimentary group in the late Cambrian, early Ordovician. This is very different to the earlier interpretations of an entirely Precambrian sequence, and it's not that easy to reconcile these young ages with the nature of the Cambro-Ordovician strata further to the south in Wales. There has to be a tectonic contact between the blue schists and these sediments, if the sediments are this young. In fact, there has to be a very large number of tectonic contacts. So to summarise the Precambrian of England and Wales, the dominant feature was a volcanic arc, indicated by calc-alkaline chemistry and the range of lithologies from basalt through to rhyolite, and this arc was active over an extended period from about 670 to 560 million years. The presence of blue schist, Alistastrome, the submarine mass slide deposits in Anglesey, suggest that there was an oceanic trench environment in Anglesey at this sort of time. And the deformation of the Precambrian rocks throughout England and Wales suggests that there was an orogenic event in the late Precambrian or early Cambrian. Almost all of these units are deformed before before Cambrian strata were deposited. This is known as the Cadomian orogeny and can be recognized as well in Brittany and in Southeast Ireland. So it's a fairly widespread orogeny. Similar rocks to the Precambrian of England and Wales are found over a much larger area, as I said, Southeast Ireland, southeastern part of Newfoundland in Atlantic Canada, and the east coast of the United States, for example, eastern Massachusetts and so on. And it is this volcanic arc terrain that extends over this large region from England and Wales through to the United States is considered to be a microcontinent with a volcanic arc on it, called the Avalonian microcontinent. The England and Wales Precambrian is very, very different from that in Scotland. In England and Wales, there is no evidence for any basements older than 1.2 billion years. In Scotland, we of course have the Lewisian basement about 2.9 billion. And at the time that this volcanic arc was active in Avalonia, the Dalradian was being deposited in Scotland, in Laurentia, and the Dalradian, as you will remember, was deposited on a passive margin, a rifting margin, as the Iapetus Ocean opened. There have been a variety of reconstructions to sort of suggest relationships between arc and trench lithologies in the England and Wales Precambrian. So here's a variety, this one suggesting southeastward directed subduction, this one suggesting northwestward, this one northwestward but quite a long way away, and this one subduction in both directions. So there's a variety of models being proposed. By and large, the further you go back in time, the harder it is to develop accurate models for how these things might be related. More recent models tend to be restricted towards southeast directed subduction zones, and these are primarily based on identifying the trench deposits in Anglesey and the volcanic arc in England and Wales. So this volcanic arc probably had a series of volcanic events, major magmatic events, 680, 600, and then 560 or so. And in the final event, the 560 event, appears to be about the same time as the emplacement of the blue schist and the Elistostrome in Anglesey. So that is this diagram here, suggesting that the Cadomian orogeny took place in the very late Precambrian, not as a collision event, but effectively like an orogeny taking place in the present day Pacific margin of North America, where you have little slices that move laterally along the Pacific margin and get accreted to the American continent. The overall plate tectonic configuration of this Cadomian orogeny and volcanic arc is suggested here. Around 580 million years, many of the continents were in a supercontinent called the Vendian supercontinent, and we have the current position of Scotland on the margin of Laurentia about there, current position of England and Wales within this volcanic arc complex about here. And since about this time, rifting was started to open the Iapetus Ocean to the south of where Scotland and Scotland and Greenland were at that time. There's Scotland, there's Greenland, there's Greenland. Okay, moving on to the younger rocks. We'll start in the Lake District, which hopefully you're moderately familiar with from the field trip. This is a simplified map, geological map of the Lake District. And you will remember that the central Lake District is largely composed of the Ordovician rocks, the Skiddaw group to the north, and the Borrowdale group to the south. Whereas the southern Lake District, this region here, is made up of Silurian and latest Ordovician sediments that belong to a major group called the Windermere group. Skiddaw group is about 5 kilometers of distal turbidites. It's very similar to those we saw in the field, muds and silts with fine laminations in places. The later part of the sequence has large slump bodies. Again, this is thought to be an olistostrome involving large kilometer-sized detached lumps of sandstone that slumped down relatively steep undersea submarine topography. Skiddaw group has graptolites that tell us that it's Arenig to Planvian in age, so early Ordovician, and they form, the Skiddaw group forms the core of a broad northeast trending anticline called the Skiddaw anticline. This anticline is a younger feature because there are volcanic rocks dipping in opposite directions either side of it, but there appears to be deformation within the Skiddaw group that is relatively early, perhaps early Ordovician in age, and it may be that this early deformation is associated with slumping in the trench environment rather than a normal tectonic deformation episode. And the Skiddaw group form these relatively rolling mountains in the northern Lake District. Icot and Borrowdale groups lie to the, respectively, to the north and the south of the Skiddaw anticline. Icot group about 3 kilometers, Borrowdale group about 6-7 kilometers. These are subaerial volcanic sequences. Okay, Icot to the north, Borrowdale to the south, and they yield Coradic ages, about 450 million year old zircon, and also Sumerian Neodymium ages, suggesting upper Ordovician Coradic in age. Rests unconformably on the Skiddaw group. And the Borrowdale group forms the rugged mountains of the central Lake District. So that's Orfeld Point. The Icot group to the north of the anticline, mostly basalts and basic andesites. So this is a histogram showing silica abundances within the volcanic rocks. Silica on the x-axis, and 60% silica is where my arrow is there, 50% is there, 70% over towards the right here. And you can see that the Icot group are largely basalts and basaltic andesites with a very narrow range in silica contents. In contrast, the Borrowdale group is much more varied. The lower part is largely andesitic. The upper part ranges from andesite through to rhyolite and is dominated by pyroclastic rocks that form in large caldera structures that include thick ignimbrites, or produce thick ignimbrites as we saw in the field, and waterlane and airfall tuffs. The Icot and Borrowdale groups have a calc-alkaline chemistry, so typical sort of chemistry that we associate with modern volcanic arc complexes. The fact that the Borrowdale group is dominated by intermediate compositions and also silicic compositions, suggest that it was formed as a mature volcanic arc on relatively thick crust, whereas the chemistry of the ICOC group suggests an immature arc on thinner crust. This diagram shows their calc-alkaline chemistry. These are compositions of ICOC and Borrowdale lavas plotted on this titanium zirconium yttrium diagram, and they all lie within the calc-alkaline field. This diagram shows lanthanum and yttrium contents, which are rare earth elements, and shows that the Borrowdale group, which are the open circles, have rather higher lanthanum, which is a light rare earth, for a given yttrium content than the ICOC groups, than the ICOC group lavas do, which are the solid circles. So this relatively subtle difference in rare earth chemistry between the Borrowdale and ICOC groups has been used to suggest that the Borrowdale group were produced further from the trench than the ICOC group, and thus give us information about the polarity of the subduction. Suggests subduction was towards the southeast. So we have a tectonic model for the Lake District in the Ordovician. In the Arenig, the upper diagram, we have a southeastward dipping subduction zone with turbidites being deposited in the trench, which now forms the Skiddaw group. Volcanism associated with this subduction took place in Wales, to the, which was then a long way to the south. In the Caradoc, or Middle Ordovician, the trench migrated towards the north. You can see in the lower diagram that the subducting slab has migrated northwards, and this allowed volcanism to take place in the Lake District, with the ICOC group here having a chemistry indicating that they were closer to the trench than the Borrowdale group there. There are very similar rocks to the Borrowdale group and ICOC group in Southeast Ireland, which suggests that the trench was striking northeast-southwest. So a northeast-southwest trending trench with subduction towards the southeast. Some recent isotopic work, largely done by me, shows that the light rare earth enrichment in the Borrowdale group are the solid, are the circles here, the solid circles and the open circles, ICOC group of pluses, and the more light rare earth enriched you get, you're accompanied by changes in the neodymium isotope composition towards the composition of Skiddaw group sediments. So it may be that the light rare earth enrichment we see in the Borrowdale group is not so much a function of distance from the trench, but more due to the fact that they were erupted through a thick sequence of Skiddaw group turbidites. This photograph is from rather higher up than we went to on the field trip, but it's the same location. It shows looking down from the mountain above where we were. There's the ignimbrites forming the edge of the uppermost part of the Borrowdale sequence, and then the Windermere group forming the lower lying land beyond. The Ordovician rocks, the Borrowdale and the Skiddaw group, underwent open folding late in the Caradoc, and as we saw in the field, this boundary here is an unconformable boundary where the Borrowdale group are overlain by the Windermere group. Windermere group ranges in age from Ashgill through to the uppermost Silurian. The Ashgill are shelf carbonates, muds and sands that we saw on the field trip at that location there, and they are characterized by a shelf fauna of brachiopods and trilobites that are high latitude. They suggest that the animals lived in relatively high latitudes and are quite different from the trilobite and brachiopod faunas we see in rocks of similar age in the southern Midland Valley of Scotland. So that's the dent group down at the bottom here. There is a rhyolite within the Ashgill, within the uppermost Ordovician, but that is the last volcanic rock in the Lake District. There are no Silurian volcanics in the Lake District, perhaps suggesting that subduction stopped by the end of Ordovician under the Lake District. Further up in the sequence, Llandafry and Wenlock rocks in the lower and middle Silurian conformably overlie the Ashgill, and there's about 70 meters of deep water graptolitic shales and silts deposited in an anoxic environment. These sort of conditions are globally very widespread in the early Silurian and are thought to represent a global transgression that follows on from late Ordovician glaciation. In the Ludlow, getting a bit higher in the Silurian, there is a very thick turbidite sequence, about 6 kilometers thick, with turbidites in the Lake District derived from the northwest, which of course is where the ocean should be. A little bit higher up in the Silurian, we move into the topmost unit in the Silurian, the Predeli. There's a change in sedimentary environment to a brackish environment with silts being deposited, shallow water silts. The whole Windermere group succession was interpreted as a fallen basin, that is a basin developed on the leading edge of Avalonia as a consequence of it being partially subducted underneath Laurentia to the north. So subsidence was interpreted as a function of Avalonia being effectively weighed down by the overriding Laurentian continent. Deformation in the Lake District. All of the Silurian and Ordovician fine-grained rocks have a strong northeast-southwest cleavage. This is visible in the fine-grained rocks, and in more competent lithologies like sandstones and lavas is less strong or even absent. Cleavage is axial planar to the folds in the Lake District, and earlier deformation events in the Lake District, the Coradic deformation event and anything that might have happened in the early Ordovician, don't have a cleavage associated with them. The cleavage cuts through all of the Lake District lower Paleozoic lithologies. This requires that the deformation in the Lake District must be lower Devonian in age. Specifically, because it postdates the youngest sediments of the Windermere group are brackish silts in the Predeli at the top of the Windermere group, which are about 415 million years. These are cleaved, so the cleavage must be younger than the uppermost Silurian. And the cleavage is also cut by the Shap granite, which is dated at 392 million years. The Shap granite is emplaced into the Windermere group and Borrowdale group, near the Windermere group Borrowdale group boundary, and clearly cuts cleavage that was formed post-Predelian age. So the fact that the Shep granite is dated at 392, which is mid-Devonian, means that that the deformation is very tightly constrained to taking place in the lower Devonian. Which, when you think about the final question of the test, which was what constraints do the southern uplands tell us on the timing of closure of the Iapetusation, remember I said that if you accept that the Wenlock rocks in the southern uplands are actually still part of the accretionary prism, then the closure must be post-Wenlock, must be latest Silurian or Devonian. Well, it looks like in the Lake District we have evidence for a major tectonic event occurring in the early Devonian. Go very quickly through the lower Paleozoic of the Welsh Basin. There's an awful lot you could say, but it's not awfully interesting, so I'll try and avoid saying it. The practical is largely on the Welsh Basin, so for those of you who feel I might be ignoring Wales, the practical's on it. The Cambrian in the Welsh Basin rests unconformably on Precambrian. The outcrops are shown on this map here. In the northwest, it's Wales. It's largely muds, a fairly thick sequence, have produced the majority of the Welsh slates. In the Harlech Dome, this area here, there's 3.5 kilometre thickness of turbidites derived from a source within the Irish Sea. So there's probably an uplifted area in the Irish Sea as a result of that late Precambrian orogeny. And in South Wales and the Welsh borders, there are thinner sequences which are largely shelf environments, sands, muds, and some carbonates. No volcanic rocks at all in the Cambrian. Right, that was the Cambrian, very quickly. The Welsh Basin Ordovician lies unconformably on the Cambrian. There was a major, there's a significant unconformity, so there was a degree of deformation in the earliest Ordovician, latest Cambrian. There was arc volcanism taking place in the early Ordovician in mid-central Wales here, at a location called Rhobog Fawr, and that is thought to be associated with subduction at the Skiddaw Trench to the north. In North Wales, there's a couple of kilometres of muds that overlie the basal shelf conglomerates and sands, and these are followed by 2 kilometres of acid volcanics in the Caraddoc, and these are responsible for the rugged topography of Snowdonia. So most of the mountains in Snowdonia are in these Caraddoc volcanics. South Wales, there's a couple of kilometres of muds with occasional turbidites, again after shelf sediments in the very early Ordovician. So Wales throughout has developed into a basin, marine basin, during the Ordovician after that early Ordovician unconformity. Again, there are some archivolcanics in the Llanfairn in this case. In the Welsh borders, there's a very thin Ordovician sequence, largely restricted to the Caraddoc, to the upper Ordovician. These are sands and muds deposited in a shelf environment, and they rest unconformably on the Cambrian. Again, their faunas are very similar to the shelf faunas of the Ashgill in the Lake District. High latitude, very distinct from the faunas in Scotland. Note the difference between the Welsh border sequence and the central Wales sequence. There's continuous deposition through the Ordovician in the centre of Wales in the Welsh Basin, whereas in the margins of this, in the Welsh borders, there is deposition only at relatively limited times within the Ordovician. Silurian in Wales, mid-Wale is largely found in mid-Wales. There's a kilometre of deep marine muds in the Llandovery, overlain by turbidites in the Wenlock, thick turbidite sequence, well exposed around Aberystwyth. In the Welsh borders, very different sequence, 600 metres only, much thinner, and largely shelf deposits, muds and limestone. And as you go up the Silurian sequence in the Welsh borders, the sea level drops, there's regression in the Ludlow, and eventually it is conformably overlain by alluvial sands in the early Devonian. South Wales, again, shelf sediments with alkaline lavas in the Llandovery, and again, there is a transition to conformable alluvial sands in the upper Silurian. So there's a transition to a terrestrial environment in the upper Silurian in South Wales. Okay, so that's Wales done. To summarise, we have strong evidence that there was an ocean between England and Wales, Avalonia and Scotland, which was part of the Laurentian continent, in the early Ordovician, as illustrated by this map. There's England and Wales, there's Scotland. The evidence for this comes from faunal provinces, which we discussed last week, and you'll empathise with your trilobite lava in the middle of the ocean. So shelf faunas of trilobites and brachiopods are different between these areas. The letters on this diagram indicate the specific nature of the faunas, specific genera that are characteristic of the faunas. Other lines of evidence that there was a substantial ocean comes from paleomagnetism, where you could use the magnetic directions preserved in iron-bearing minerals in sediments, but particularly in volcanic rocks, to look at the location of the poles at the time, or relative location of the poles. And this suggests that Scotland was at a latitude of about 10 degrees south, as is shown on this diagram. That's 30 degrees south, so that's the equator, so Scotland about 10 degrees south, whereas England was located about 60 degrees south. The two regions, if you look at the apparent polar locations up through the lower Paleozoic stratigraphy, they had different behaviour. They clearly were on separate continents. Other less good evidence for an ocean: in the southern uplands we have lithologies that resemble mid-ocean ridge basalts. The southern uplands indicates a north-dipping subduction zone, the structure of the southern uplands in the Caradic. The Lake District suggests a south-dipping subduction zone in the Caradic. And finally, in northwest Scotland and in the Midland Valley, we have tropical type carbonates in the Caradic, whereas in the Welsh borders at this time there were relatively high latitude carbonates. England and Wales and Scotland had a radically different Precambrian history. England and Wales, as we've seen, were an active continental margin with subduction to underneath England and Wales in the late Precambrian. Scotland in the late Precambrian was a passive margin with Dalradian deposition in rifted basins. After the Cadomian subduction terminated in the late Precambrian, England and Wales were briefly a passive margin through the Cambrian, and then southeast dipping subduction recommenced in the early Ordovician. The Aachen Trench moved to the north to the Lake District in the Cyrillic, and Wales, the Welsh Basin, opened as a result of back arc spreading. In the uppermost Ordovician, subduction to the southeast terminated. There's no evidence of arc volcanism in the Silurian at all, so subduction presumably terminated in the late Ordovician. An interesting observation is that the Lake District volcanics, the ICOC group, are only 40 kilometers from the first outcrops of the southern belt of the southern uplands. So that's quite a narrow, quite a small distance compared with the distance between the trench and the volcanic arc in most modern arcs, which is typically around 100 kilometers. So an interesting question is, where has the Lake District forearc gone? We'll discuss this next week. In the later sequence of the late Silurian sequence of the Lake District, we start to get turbidites derived from the northwest, derived from Laurentia, suggesting that the Lake District and Laurentia were in close proximity in the upper Silurian. And we know that the main deformation in the Lake District and also in Wales is mid-Devonian in age. And that's it. Good. Right. Thank you. So, feel free to have a coffee, orange juice, tea, or whatever. And the practical consists of a single map this week and a handout which is located.
Ask him about that.
I'm gonna go